scale relativity is a geometrical and fractal space-time theory. The idea of a fractal space-time theory was first introduced by Garnet Ord, and by Laurent Nottale in a paper with Jean Schneider. The proposal to combine fractal space-time theory with relativity principles was made by Laurent Nottale. The resulting scale relativity theory is an extension of the concept of relativity found in special relativity and general relativity to physical scales. In physics, relativity theories have shown that position, orientation, movement, and acceleration cannot be defined in an absolute way, but only relative to a system of reference. Noticing the relativity of scales, as noticing the other forms of relativity, is just a first step. Scale relativity theory proposes to make the next step by translating this simple insight formally in physical theory, by introducing explicitly in coordinate systems the state of scale. To describe scale transformations requires the use of fractal geometries, which are typically concerned with scale changes. Scale relativity is thus an extension of relativity theory to the concept of scale, using fractal geometries to study scale transformations. The construction of the theory is similar to previous relativity theories, with three different levels: Galilean, special and general. The development of a full general scale relativity is not finished yet. However, the existing progress and results already have consequences for the foundations of quantum mechanics, particle physics, and high-energy physics. Furthermore, empirical predictions in physics, astrophysics, and cosmology have already been validated, most often with a high precision, or highly statistically significant results. History. Feynman's paths in quantum mechanics. Richard Feynman developed a path integral formulation of quantum mechanics before 1966. Searching for the most important paths relevant for quantum particles, Feynman noticed that such paths were very irregular on small scales, i.e., infinite and non-differentiable. This means that in between 2 points, a particle can have not one path but an infinity of potential paths. This can be illustrated with a concrete example. Imagine that you are hiking in the mountains, and that you are free to walk wherever you like. To go from point A to point B, there is not one shortest path but an infinity of possible paths, each going through different valleys and hills. Scale relativity hypothesizes that quantum behavior comes from the fractal nature of space-time. Indeed, fractal geometries allow to study such non-differentiable paths. This fractal interpretation of quantum mechanics has been further specified by Abbott and Wise, showing that the paths have a fractal dimension too. Scale relativity goes one step further by asserting that the fractality of these paths is a consequence of the fractality of space-time. There are other pioneers who saw the fractal nature of quantum mechanical paths. Also, as much as the development of general relativity required the mathematical tools of non-Euclidean geometries, the development of a fractal space-time theory would not have been possible without the concept of fractal geometries developed and popularized by Benoit Mandelbrot. Fractals are usually associated with the self-similar case of a fractal curve, but other more complicated fractals are possible, e.g., considering not only curves, but also fractal surfaces or fractal volumes, as well as investigating fractal dimensions which have other values than 2, and which also vary with scale. Independent discovery. Garnet Ord and Laurent Nottale both connected fractal spacetime with quantum mechanics. Nottale coined the term scale relativity in 1992. He developed the theory and its applications with more than 100 scientific papers, 2 technical books in English, and 3 popular books in French.